before the break, we looked at the concept of autoencoders, which are essentially regular neural networks. They are trained just like 100% exactly like a regular neural network. So for example, if we are doing MNIST-based autoencoder, inputs will be 700. Okay, we don't have to directly go to 100 neurons. We can also make it a multi-layer. For example, we can make it go to 500 neurons, then 100 neurons. So this concept is called stacked autoencoder, or a deep autoencoder, however you want to think of it. Okay. Then during training, like I said, we'll do the reverse. From 500, as we go to 100, we'll go to 500. And then we'll go to 784. So let's briefly talk about how will we train it. Okay. If we wanted to create a multi-layer or a stacked autoencoder, okay. So it's typically, if we try to put the whole thing together and do a backpropagation on it, for 2 layers it might work, but if we wanted to add a 3rd layer over here, it usually will not do as good of a job because the gradients become too small, or for whatever reason it doesn't work as well, right? So the idea in training is to train it piecewise. Okay, what does that mean? Just train it on compressing to 500 and decompressing it. So the way you will do it is, okay, so you'll start with 784. Okay, you'll compress it to 500 and then decompress it to 784. So you'll train it on the entire data set. After it has learned training, then basically you'll fix the weights over here.
Do we do that by pickling?
You can do it through pickling, yes. So anyway, the weights are now fixed over here, right? And we remove the output layer. Okay. So then what we do is we go to the next layer now. So as you can see, now think of the second problem as input is 500. Okay. Then we compress it to 100 and decompress it back to a 500. Okay. So now we are focusing on learning these weights over here. Okay. How do we compress? How do we decompress? So where will the training data come for this part? Can you guys see?
The output of the previous.
Output of the previous. So feed in any digit, whatever the 500 values are, it produced, feed it over here. Same thing becomes the expected output over here. And keep going through it. Once it's trained, then what do we do? Remove the output layer. So then this becomes our, so now we have fixed these weights through the second step, fix these weights. So now we can compress anything. And typically what we do is after we have created this part, then we fine tune it. Meaning now we further train it by initial weights that we had obtained from this part and this part. So those are the initial weights. And then we train it again. We feed in the entire data set, input to output. It goes and learns and adjusts these weights. So now we can have an easily stacked autoencoder. Okay. So to summarize, we have 3 options typically with data. So let's take a look at our classification problem. Okay, so we have usually 3 approaches. Let me make it 4 approaches. Okay, number 1 is direct data as input. to the classifier. Okay, so for example, all 784 go in. Then we'll have some hidden layer and some output layer. So this will be approach 1, right? Approach 2 is do some dimensionality reduction. So dimensionality reduction via PCA or LDA as an example. Okay, so for those of you who are in computer vision, we've talked about the PCA algorithm. So in this case, the approach will be like this. We take the 784 inputs, we apply principal component analysis, and let's say this will give us 100 dimensions. So data in 100 dimensions or 100 numbers. Then we feed those 100 numbers to a neural network classifier with one hidden layer. And then we will do the classification. So this will be approach 2. Here, third approach will be autoencoder based. Okay, so we feed in 784. Okay, and then through the encoder, pretend it's already trained, we get 100 numbers out. Regardless, this is a single layer or multiple layers over here, it doesn't matter. Well, it matters depending on the data. Multiple layers will give you more accuracy. Okay, then we feed in to a regular neural network classifier or support vector machine or one of those, and we classify. So that's the third approach, right? Fourth approach is we feed it to a Siamese CNN. Okay, we flatten it, we reduce the dimensionality to 100, and again, once the Siamese has been trained properly, we use the output of the Siamese as input to a classifier. So that's the fourth approach. Which one of these will produce the best result? Okay, and again, it's a little bit of a function of the data set, but majority of the time, especially with face recognition, this is the best approach. Okay. What will be the second best?
PC.
Okay, the second best turns out to be the autoencoder based. So this is the second best. And sometimes it is the best, again, depends on whether a CNN and whether we have enough pairs of training data or not. Okay, this autoencoder over here, the encoder part, actually somebody has done a mathematical analysis of this part. And this one basically does what is called a nonlinear PCA internally. Okay, and nonlinear PCA, see in PCA, again, those of you who were in the computer vision class, PCA basically creates basis vectors which are orthogonal to each other, meaning 90 degrees, right? But a nonlinear PCA also produces orthogonal things, but these are surfaces, meaning here could be one surface, then here could be another surface. So it maintains the nonlinearity while keeping orthogonality. So it is better than what we call a traditional or the linear PCA. So this one would be the next best approach, right? And of course, then comes the PCA, and then comes the regular classification, okay? So now let me introduce one more advanced concept.
For semis, here we do like verification using CNN, right?
Correct.
We can use something different than.
Okay, so to clarify this part, when we are building the CNN, we'll train it using verification. So, meaning again, pretend this is CNN1, this is CNN2. We feed in two different images. Okay, we create some vector, then we feed it to some DW and so on. So we train it like this, similar, dissimilar, similar, dissimilar, right? Remember, as we discussed, the weights are shared. Okay, once it's completely trained, then it has fixed weights. Then we don't worry about the second part. We don't worry about feeding two images. We only feed single image. That single image produces, for example, 100 outputs. And as we discussed, that represents a point in 100-dimensional space. If there's another two later on we fed, that will also be very close to over here. So all the twos will be clustered, all the threes will be clustered, right? So, and so on, the fours and so on, in this 100-dimensional space. Because it's already pushing them away from each other, the dissimilar are pushed away, the decision boundary can be nicely created by this neural network classifier, so it does a better job.
Okay, but we can't, we choose CNN because it makes feature extraction, so the verification can't be only done with CNN. You can't choose any different.
We could have picked like a regular network over here and have it create the distance on the same loss function that we discussed. But CNN, a deep CNN, will do much better job of recognizing features and then flattening and then compressing will create compressed data which highly distinguishes between two different classes. Okay. So CNN is not a requirement over here for a Siamese network, but all implementations, as you will see, CNN works better than a regular neural network.
Because of the feature extraction.
Because of the features.
Okay, for the autoencoder, it is unsupervised learning, right? So
Up to this part is unsupervised. Then once we tie it to a classifier, it becomes supervised. Because we have to adjust the weights over here, right?
okay, so if we want to do like unsupervised only, is it possible?
For recognition?
It will not be, because we have 10 classes, right?
Yeah. Okay,
For
so
the autoencoder, like last question, the input and the output has to be the same when you are doing the training.
Yep.
First, if we are using the MNEST database, does it have to be exactly the same picture, or could it be like a different, let's say for example, tool? Does it have to, can it be a different tool but slightly different?
Yeah, so good question. Let me explain. There's two types of autoencoders that we typically use. One are what we just discussed, the same input, same output, right? So the expected output is 100% same. Okay, there's also what are called denoising autoencoders. So in these ones, what we do is, on purpose, we feed in a noisy image. So if it's a person or a scene or whatever, so we add noise to it on purpose. The expected output is supposed to be a clean output. So this way we are making it learn how to ignore the noise or slight variations in the data. Okay, so now let me come to an advanced concept, which is pretty neat. So in my opinion, whoever came up with the autoencoder also should be given, the variational autoencoder should be given another Nobel Prize, okay? Because again, the concept, the theory is pretty neat, even though the final result is pretty easy, but how did somebody come up with this, is amazing. Okay, and the applications of this, these are amazing. Okay. Okay, so first let me explain the central idea. The idea is like this. Okay, let's say we compress. So we have some input, regardless it's a face or a person or a MNIST digit or whatever, right? We come up with compressed data. Okay, now we decompress. So this is doing the compression, this is doing the decompression. People don't use compression or decompression usually. I tend to use them. People use the term encoding and decoding. But in my opinion, it's really doing a very smart compression so that we can recover the data from it, right? Okay, so now let me ask you a simple question. Suppose we feed in image of a person. Okay, it produces some 100 numbers, then we decompress it, we get the same person back. And we train it on many, many images, and suppose it's ready, it has learned how to compress, right? Okay, so now we do the opposite. We feed in an image, suppose this is I5, some person, right? Okay, it will produce some 100 numbers over here, right? Okay, so what if I remove the compressor now, or the encoder now? What will happen if, so if I feed in 100, it will produce similar to I5, correct? Slightly blurry, but similar image as the input. What if I slightly change this data? Change the compressed data. Okay, what would you expect the output to be? Will it still be the same person, or it will be totally different, or?
Close,
Similar.
be close.
Okay, and the answer is, if most of the time it will be totally different, okay? Because, or may not even look like a person, okay? And the reason is because this is not a continuous space over here. Okay, everybody has a certain vector in the in these 100-dimensional space, which represents that person, right? The way this has been designed is only to operate on those known 100 vectors to be able to recover it. Okay, but the concept in variational autoencoder is: what if we create this compressed scheme such that this compression produces a continuous space? Okay, then from this continuous space, if we sample any data, like any 100 numbers, then that will create a variation of, depending upon how different this is, it will create a variation of that person or that image or something, right? So the person who came up with this whole theory, their idea was like this. Okay, see, there's a field of machine learning, which is becoming, or actually has always been that way. Okay, so there's a basic machine learning, which we have done so far, or deep learning, and there's the advanced machine learning, right? Majority of all the advanced concepts in deep learning, machine learning are based on statistics. So we call it statistical machine learning. So this is where the math becomes a little intimidating and it's hard to visualize what we are doing. But don't worry, I'll give you a nice intuitive explanation of this so that it makes perfect sense, so that we can understand all the math behind it, why we are doing it, and hopefully some of you will continue and be able to come up with some super amazing new discoveries out of it. So anyway, coming back to the variational autoencoder, the idea is like this, right? If we take a look at our data set, right? Okay, forget this for a minute, okay? Let's take a look at basic statistics. Suppose you were looking at test scores. Pretend there are 100 students in the class, okay? So pretend the average in the test is 70. So then what would you expect? A lot of the students to be close to the average, right? So there might be 73, 77, 78. Okay, a few students will be 98 or so on. Few students will be, 20 or 35 or so on. But a lot of data will be clustered over here. You guys agree? So if we treat it as a probability distribution, what will this Gaussian distribution, right? So it will look something like this. So if the mean is 70, right, depending upon how the test was hard or difficult within a standard deviation, so the width of this Gaussian will be dictated by the standard deviation as an example, right? So anyway, so in statistical machine learning, okay, if you take a look at data set, just like test scores are data, and they follow a distribution, right? So same way, whatever 50,000, 60,000 images we had, okay, remember they are points in a high dimensional space. Just like this is a single point in a one-dimensional space, right? So will they follow certain kind of distribution? Perhaps, right? Could be uniform, could be Gaussian, could be gamma, whatever. But anytime data is involved, we can represent that data by a distribution. So the idea in a variational autoencoder is, let's transform this distribution. So there's a distribution over here. Okay, as we compress, this data will have another distribution as well. But if we can make this distribution from this input distribution, we can make this, let's say, a normal or a Gaussian distribution. So let me summarize the idea again. We feed in data. We want to make this compressed data follow a normal distribution. Okay. And because normal distribution is a continuous distribution, then basically if we sample from this normal distribution, we can generate artificial data over here, which will be very meaningful. So that's the idea behind a variational autoencoder. Transform into a continuous distribution so that even though in the beginning their data is over here, so what I'm trying to say is, in case of test scores, even though this is the data that we were given training data, but after we know it's a Gaussian distribution, we can easily pick another data here, another data here, another data here. Okay. Let me see if I can give you an analogy. Okay. Let's pretend all the high scorers are very nerdy looking. Okay. So if we feed in, let's say, so suppose we have trained it, right? Okay, now suppose we sample this continuous distribution, meaning in case of test score, we feed in a 96, but it was never part of the original data. So the image, if this is producing an image, what would it look like? Like an athlete or like a nerd? So this is how you can sort of see that what variational autoencoder is. like once this is in continuous space, then from here, we can create variations of nerds, variations of athletes, or normal people, or whatever we feel like it. So that's the beauty of this technique. Especially in deep learning, data is very, very important. More data we have, we can train systems to do better recognition. So I'll come to that part. So now the challenge over here is, the biggest challenge is, how do we force the input data, which is following a totally different distribution? We don't even know what that distribution is. How can we, as we compress it, make it follow a Gaussian distribution or normal distribution? Sorry, normal is same as Gaussian, or gamma distribution, or exponential, or distribution. So how do we force this compressed data to follow a distribution, right? So let me give you a hint now. So what does our loss function typically do? Our loss function guides the training so that we can accomplish that goal, correct? So in this case, what will the loss function try to do? Make this distribution close to which distribution?
Normal distribution.
Normal distribution, okay? So just like if I gave you 2 points, if I wanted you to tell me how close or how far they are, what measure do we use?
Euclidean distance.
Euclidean distance, right? Now, we're not talking about a single point, we're talking about distribution of data. Okay, so my question is, how do we indicate, or how do we know that these two distributions are close to each other or far from each other? So this is where the KL divergence comes into play. Okay, so in statistics, there's a measure for measuring the similarity of distributions. Okay, so the formula looks something like this. Okay. Okay, suppose we have some distribution P of x, some distribution Q of x. Okay, we indicate the similarity through, again, a distance measure. So the answer will be a scalar, exactly like a distance, like a number. Okay, so basically, KL basically means KL divergence. Okay, D for the distance. Or divergence, however you want to think of it. So these are the two distributions. Okay? So the formula goes something like this: summation log of P of x. Sorry, it goes like this: P of x log of P of x over Q of x. Okay, so that's the formula for two distributions. Okay, so before we go further and try to understand the variational autoencoder, in my opinion, okay, especially if you're new to this, let's try to really understand, how does it compute? Okay, so let me go back over here. Okay. If I gave you test scores like this, okay, just by looking at the data, how would you tell it's a Gaussian distribution?
By the concentration.
So
Okay.
and sigma.
So, or if I gave you, let's say, some other data, and the beta distribution looks something like this. So it could be like this. So anyway, how would you tell just by looking at the data? Is it following beta distribution or Gaussian distribution. Okay.
High frequency as the mean. So it's
Okay, so the important concept is that you have to do what's called binning. Okay, only if you do binning, you'll be able to see what kind of distribution it is. Okay, what exactly is binning? Basically a frequency count. Meaning how many times each data is appearing, right? So if I picked a bin size of, let's say, 10, meaning 0 to 10, then 11 to 20, or 21 to 30, right? And if I counted how many numbers are appearing within that range, then for test scores, what will you see? Around 70 to 80.
Is it like a histogram?
It's exactly a histogram. So, so you will see a high number appearing between like a 70 to 80 range, then 60 to 70 will be a little bit less, 80 to 90. So basically this will come out something like this. Okay, so after we know, within a certain range, how many times the frequency of the data is, then we can easily see the distribution, right? So anyway, as you try this, okay, you have to have, so let me see if I can quickly show you a little bit of the code. Okay, and whatever I'm showing you, I'll put it on the website. So, let's see. Okay, so, I'll put some code on the Python code, very simple code. Okay, so we program this formula. Okay, we give it some distribution of data, where there might be like, let's say, a Gaussian distribution, some numbers appearing closer, some numbers appearing farther, right? So as we program this, what you will see is, so first of all, a few properties of the KL divergence. It's always positive. Okay, this is not symmetric.